So here we want to determine how the graph of a rational function is going to behave as x is approaching positive infinity and as x approaches negative infinity. So in other words, we are looking at the end behavior of rational functions. And we call these horizontal asymptotes. Now, the line y equals d, where d is a constant, is called a horizontal asymptote of our graph f if the y values f of x are approaching this constant d as x approaches positive infinity or as x approaches negative infinity. So there's several different cases that we need to consider here to help us better understand these horizontal asymptotes. So first, let's suppose that the graph of the rational function looks something like this on the left-hand side of the y-axis. So observe that as x is approaching negative infinity, the y values are approaching that line y equals d, but never crossing. So using our infinite end behavior, we can say that as x is approaching negative infinity, y approaches d, or f of x is approaching our constant d. Now, alternatively, on the left-hand side, we could have the graph of the rational function looking something like this. And just like with the first case, as x approaches negative infinity, these y values are approaching that constant d, but never crossing. So we can actually use the same infinite end notation that we did in case 1. Now, moving to the right-hand side of the y-axis, we could have the rational function looking something like this. And here, as x is approaching positive infinity or growing without bound, the y values are approaching d, but never crossing. And last but not least, we could also have on the right-hand side of the y-axis, the rational function might look something like this. And again, as x is growing infinitely large without bound, the y values are getting closer and closer to our constant d, but never crossing. So again, we can use that same infinite end notation as the first case. Now, keep in mind that rational functions are ratios of polynomial functions. And with polynomial functions, we determine the graph's end behavior by using the leading term. So since rational functions are ratios of polynomials, it makes sense that we're going to use the ratio of our leading terms to help us find these horizontal asymptotes. So let's go ahead now and establish some algebraic procedure for finding these horizontal asymptotes. So to help us in identifying horizontal asymptotes, let's begin by considering a rational function defined by this ratio of polynomial functions. Now, keep in mind, all of these a values and all of these b values are the polynomial's coefficients, or real numbers. And also keep in mind that these powers on x, these n terms and m terms, these are the exponents and they must be whole numbers. So 0, 1, 2, and beyond. Now, to help us in identifying the horizontal asymptotes of these rational functions, we want to consider the ratio of the leading terms of the rational function. Now, from this ratio of leading terms, I want to point out the degree in the numerator and the degree in the denominator. So n is the degree of the leading term in the numerator of our rational function, and m is the degree of the leading term in the denominator. Now, there are 3 different cases here when comparing these leading terms that we need to consider. So case 1. So in case 1, when the degree in the numerator is greater than the degree in the denominator, our rational function has no horizontal asymptote. Now case 2. Now in case 2, when the degree in the numerator is less than the degree in the denominator, then we know that our rational function is going to have a horizontal asymptote at y equals 0, or in other words, at the x-axis. And we're familiar with this example, or this case. An example of this case is the reciprocal function. So as we saw earlier, the reciprocal function has a horizontal asymptote along the x-axis, or y equals 0. And last but not least, case 3. So in case 3, when the degree in the numerator is equal to the degree in the denominator, we can conclude that our function, our rational function, is going to have a horizontal asymptote at the ratio of the leading terms. So this is going to produce a constant value. So for example, if we look here at this rational function 2x minus 1 over 4x plus 3, notice that the degree in the numerator is 1 and the degree in the denominator is 1. So looking at the ratio of our leading terms, we can conclude that this function is going to have a horizontal asymptote at the ratio y is equal to 2 by 4, which of course simplifies to 1/2. So now that we have explored the procedure for finding these horizontal asymptotes in a little more detail, we need to proceed in finding and exploring our single remaining asymptote, slant asymptotes.